Hi, my name is Murthy Yapmak. I'm an applications engineer in Keysight Technologies. In this short video, I'm going to show how to set up the dual polarization in a receiving phased array antenna. As you can see, this schematic is from System View, one of the system simulators from Keysight Technologies. And what we see here is on the left-hand side is an array antenna. We can define the array geometry. For example, here we defined a 4 by 4 rectangular array. Now we have to define both the polarizations. So this behaves as if we have two antennas per location. So we specify two antennas per location. So it behaves as if there are 16 antennas. And so we will get 32 outputs from the antenna array here. So each element, what type of polarization will it be? As we saw, 16 of them are one type of polarization and other 16 are other type of polarization. These two types of polarizations can be E theta, E phi. They can be left-hand circular or right-hand circular. Or you can even specify the axial ratio for the ellipse to specify the polarization between them. Here, what we are doing is we chose an antenna, cosine type of shape of an antenna, the beam pattern, and we defined one type of antennas, one set of 16 antennas, all having E theta orientation only, and other 16 having only E phi orientation. So when an incoming wave comes, we should define the polarization of the incoming wave as well, so that the antenna will be able to react to the incoming wave. We chose the incoming wave to have only E theta polarization in this case, no E phi. All right, so we got 32 outputs coming out of the antennas, and these 32 will go through 32 amplifiers and 32 phase shifters. In this phase shifter in system view, if you specify the direction of the beam in which the beam is coming towards the antenna, it will form a beam towards towards that plane wave so that it maximizes the energy. So the main lobe will be formed in the direction of 10 degrees azimuth and 10 degrees elevation. Now, what it does is it will compute the phase shifts on the signal such that the beam is in the direction of 10, E theta 10, E phi 10. So it computes 32 phase shifts and applies them to all the 32 inputs. One set of phase shifts, PH1, are all applied to the one type of polarization. The other PH2 will be applied to the other type of polarization. They go through a array attenuator. We chose not to do any windowing here for simplicity. Then it goes through a power combiner. So one of the things that we would want to notice and then watch and understand about the polarization is to be able to tap these two 16, one set of 16 into one output, another set of 16 into another output. The way we do that is by defining a custom mode for the power combiner and telling the combiner to combine all the 16 of one type into one output, other type, all the other 16 into another type. This is done through a element map as shown here. The element map typically looks like the one that's shown here. So what happens is all the ones, all the odd rows will be combined into one output. All the even rows will be combined into another output. So we get two outputs. We will be able to see the polarization discrimination at the two outputs. Of course, at the end of the day, we want to combine the signals from both the sets of antennas and send them into the receiver to maximize the signal to noise ratio. Let us examine the polarization discrimination at the output of this first splitter, array split 1. So let's go ahead and simulate it. It will be a very short, very quick simulation. And we see the data set. Now, before examining anything, let us set up let us set up the expectation. So because the incoming wave is all E theta oriented, only the E theta oriented, E theta polarized antennas will be able to produce an output. E5 oriented antennas will not be able to produce an output. That means out of the two outputs at the array combiner that we saw, we get only one output. So the way to examine that is to look at the node information, and then let us look at the node information signal at the array split 1. As you can see, this is a voltage, and it's a complex voltage. We produced only E theta voltage. E5 antennas did not produce any output. You may ask, will I be able to get the discrimination if I switch the incoming wave polarization to the other one? The answer is yes. We can quickly examine that by doing reversing the incident wave and then simulating and then noticing that we now got the other antennas, E5 antennas producing output. What if my incoming wave has both the polarizations? Will these antennas react to that? Let's examine that as well. So let's say both the antennas have equal contributions to the signal. Both the polarizations are equally contributing. Now, if we simulate again and then watch, we got outputs on both the antennas. So this clearly you can use this polarization discrimination to your advantage for taking advantage of the polarization diversity in your communication system. Now, the final note, you may say, I really want to send each polarization into different receivers. Unfortunately, in this schematic, in this implementation, we can place only one receiver. If we want to send the signals into two different receivers and then form two different beams in different directions for each polarization, if your application demands that, please look out for another video where I will describe exactly that process. Thank you very much for watching the video.